All right, here we go. Welcome to this talk. This is Anatomy of a Bare Metal Synth. I'm really excited to talk about this today. My name is Jack Campbell. I'm a senior software engineer at Universal Audio. I work on native audio plugins for the most part, mostly on Mac and Windows, which are notably not embedded devices. So really not what we're talking about today. I've been tinkering with embedded stuff over the past 5 years or so, and I have had the opportunity to work on some Linux devices and bare metal devices and learn a lot about embedded during my time at UA. And I noticed that there wasn't a lot of resources, I think, for this exact situation, this particular, I knew how to code, develop audio software, but I didn't know anything about embedded stuff. And I figured a lot of other people might be in that boat and might be embedded curious. So I wanted to make this talk to kind of share what I learned along the way, maybe to kind of put some things into context. I think there's a lot of resources for if you are like a maker and you are working with the Raspberry Pi and you want to write Python and make something really cool, and all that is great. Or there's a lot of stuff, I think, for electrical engineers who want to learn how to code. But for this particular example of people who are familiar with native software, this talk goes out to you. I'm going to start with kind of the landscape of embedded software so we can put into context the program that we'll be describing today into the greater embedded software world, and where you can kind of go from there. We'll talk about this bare metal synthesizer kind of as an example and an excuse to throw out a lot of jargon. We'll talk about the MIDI circuitry going into the synth, and then what that MIDI actually becomes. It becomes UART. We'll talk about what UART is. And then that UART ends up being parsed in our software, and things will start to kind of probably look a little bit more familiar. We'll have an audio program that reacts to that MIDI, generates audio while the audio hardware is requesting samples. That audio will be turned into a digital audio stream, which we will then turn into an analog audio stream and amplify and throw out to the world. And then from there, I'll just kind of show where you could go next if you wanted to tinker with this stuff on your own. It's a lot of stuff to get through in one talk, but we'll do our best. I really just want to have the excuse to put GPIO, DMA, I2S on a slide, all these things that may not be familiar if you've mostly done native software development, and just make them more Googleable or DuckDuckGoable in the future for you. I think there is certainly a learning curve to all this stuff, but it's not as scary as it seems, and so I want to demystify some of that. We're going to be using the Electrosmith DaISy seed as our little development platform here. I'll describe more about what that is, and we'll be writing in C++, and I'll kind of talk about what bare metal C++ is and how it might be a little bit different from what you're used to. Also, analog electronics are going to be pretty relevant for this talk. It's not a prerequisite per se, though I won't necessarily go too deep into the analog electronics. I'll just mostly, multiple times throughout this talk, recommend this book, Make Electronics by Charles Platt. It's a great read. I've read it a couple of times. It's got all this stuff from these bullets here. It teaches you how to solder, which tools to buy, how to buy components and put together your lab, how to not go crazy with plastic bags of resistors all over the floor. You really want to get an organizer. Like, that should be the first thing that you get. And it just does labs. It's not really textbook style. It has you blow up a resistor in the first lab. Spoiler alert. Or blow up an LED because you don't use a resistor in front of it. Stuff like that. It's a really neat little book. And then there is a lot of stuff on the SparkFun site. I'll be probably name dropping them quite a bit since they're local. They're here in my hood in Colorado, up in Niwot. And they have a lot of articles about digital electronics in particular that don't get covered as much in that Make Electronics book, but digital electronics are also something you want to know about. So you kind of want to get to the point where you can look at a schematic like this one. You can see those little squiggly lines there. That is a resistor. I can't remember. I think sometimes you'll see it as a little box, a rectangle. One of those is maybe, well, I don't want to say something wrong, but you'll see those interchangeable. One of them is considered old school, and I can't remember which one it is. But then, there's capacitors on there. There's an op amp in the middle. Looking at that and then being able to implement it on, a breadboard is what this thing is called. You don't need to solder any of these connections together. You just plug things in kind of like Legos. It helps to get to that point. And then from there, you can actually solder stuff together and make projects that won't fall apart if you put them in on an airplane or whatever. So kind of back to software. Bare metal programming is what we're going to be talking about today. I kind of consider it a good basis for embedded software because the concepts that you would have to learn in order to do bare metal programming apply to a lot of the other types. And in this type of programming, you're talking directly to hardware registers in your code, and that's the part that makes it a little bit different from native programming. And while you could do everything just by writing to memory mapped registers directly, vendors such as ST Microelectronics, in the case of the DAISY's MCU, will supply a library known as a HAL, or a hardware abstraction library, that covers it for you. But in your debugger, if you've got a JTAG debugger connected to your board so that you can step through the code, you can step right through to the actual line of code that is writing to the hardware. So that's what kind of puts it apart. There's no OS in the way abstracting all that stuff from you and stopping you from shooting yourself in the foot. On the other end, you've got embedded Linux, which you're still dealing with analog circuitry, talking to a microcontroller likely, or something like that. But you've also got big old Linux running on the board, relatively big compared to bare metal. So you've got the OS overhead, not only of the runtime overhead, but also the learning overhead and the having to build Linux from scratch. And you can't, talking directly to the hardware is a little bit less direct than in bare metal. You can write drivers and include it in your Linux distribution, or you can use the device tree to interact with the hardware more directly. But there's more to do than just literally writing to a register. One of the big draws of embedded Linux, and I think one of the most powerful aspects of it, is that if you have a code base that is running on a native platform like Mac especially, or native Linux especially, Windows to a lesser extent, you'll have a harder time. You can port that to an embedded situation without having to rewrite everything from scratch. And that's a huge draw. We've benefited from that a lot at Universal Audio. A lot of our embedded products run on Linux, and they're based on code that was written on Mac and Linux and Windows. I also want to mention, just because you'll come across these other types of embedded software development in your Googling, I just want to mention them. RTOS, or free, usually free RTOS-based programming, is basically, it's closer to bare metal than it is to embedded Linux, I would say. It's free RTOS is basically like a really good thread library that allows your program to have deterministic timing and conform to real-time constraints. So it's not an OS in the same sense that Linux is. It doesn't give you a file system and all that stuff. Or you might come across FPGA programming, which I've always thought sounds really cool, and I have never done it myself. Instead of writing a program that it runs on a CPU and you're giving instructions to be interpreted one by one, your program is written in what's known as a hardware definition language, which actually defines the topology of logic gates on a board, a field programmable gate array. Maybe one day I'll know stuff about that, but today I do not. So you can try asking questions, and I'll say I don't know. So that's kind of where we're at. We're gonna talk about the first one, bare metal programming, and that's what our synthesizer is going to be. It'll be built on this DaISY seed, which is an embedded SOM, or also known as a system on module for music applications. It's a consumer-facing type of product, similar in motivation to the Arduino, the Teensy, the Raspberry Pi Pico, not the other Raspberry Pi, which is an embedded Linux device. This is there's a microcontroller and some other stuff on there for you, all put together in one nice package with some software libraries that's meant to be easy to use for people who just want to build something fast. The thing that sets the DaISY apart is that it has an onboard audio codec. At the time that I wrote these slides, it was an AKM audio codec. I'm not sure if it still is, but it's neither here nor there. As some people may know, it's difficult to get AKM chips. It has been for a little bit here, unfortunately. But there's an audio codec on there, and you don't need to hook up a separate one, and that's a big draw. You can just write a program, put 2 wires in there for a stereo audio signal, and get it out, which is great. There's also onboard RAM, quite a bit of there's 64 megabytes of onboard RAM, which is good for audio, where you might have to have large delay lines, store samples in memory. That's kind of a good differentiator. And then the MCU is pretty capable for writing some mid some audio programs that need to do some fancy stuff. The STM32H7 series, which has the ARM Cortex M7 CPU on it, and an MCU or a microcontroller really is, it's got the brain, which is the CPU, and then it's got these I/O peripherals and interfaces that it uses to interact with the outside world. And so it's got an audio interface on it, and we'll talk about these communication protocols later that it uses to talk to other devices. And then another nice thing about the DaISY is the software ecosystem that it provides. It has this thing called libDaisy, which it uses to wrap all of the STM32 HAL hardware abstraction library calls. So you can write everything in C++. You could before as well, but it wraps all the C stuff and offers audio-specific wrappers. Usually in a hardware library, you might get a pre-built UART library that allows you to use UART. But here you get a layer on top of that. You get MIDI support, which is great. You might not get that in a lot of other libraries. Or there's audio support. Is kind of a first-class citizen in this library. We will be digging a little bit much of this talk will be digging into libDaisy and seeing how it's doing what it's doing. Less of this talk will be going into the DSP library, but I do want to mention it. This is not a DSP talk necessarily, really at all. We talk a little bit about how the audio is created, but it's not the focus of this talk. But this DSP library vendored by DaISY is really nice. I've used it in Juice plugins before for hobby stuff, and it's really portable and small. It's got your basic food groups in it, filters, oscillators. It's got some nice reverbs in there, and we use it to make our program pretty small without a lot of doing our own DSP. I want to, on this slide, kind of show you how libDaisy, how the calls go from your code all the way down to what might look less familiar, the actual bare metal code, what makes this stuff bare metal. Your client code in the program, which is on GitHub, and I'll show more of it later, but here's just a little snippet of it as an example. We've got an audio callback here going into libDaisy through this DaISY seed handle. And then libDaisy has some kind of other C++y stuff that kind of maybe looks like what you're used to. You got the audio callback going in and being passed to a DMA handler. We'll talk about what DMA is. And then it goes to this C layer, the STM32 HAL. Here we are starting a DMA transmission with the serial audio interface, the SAI, which again, we'll talk about more later. And then the lowest level, right under, being called directly by this HAL function, is we have a memory mapped interface, so like a pointer is how we use it in the code, that HSAI handle to the serial audio interface. We are writing to a register on the hardware directly, control register 1, CR1 there. We're writing the SAI enable bit. And that's kind of what makes this code different than native programming. We're just, a couple steps down here in the call stack, we're directly interfacing with the hardware, which is pretty cool and exciting. This is what our synthesizer is going to look like. It's just a flow diagram, not a schematic, but you'll see we've got MIDI going in there. The MIDI will come in, it is UART in this case, and it will be, it'll be picked up on that RX pin, sent into our program, sent out. Digital audio data will be generated in response. You'll see those 3 wires coming out of the serial audio interface there, being converted to analog audio via the codec and then amplified. And then this is a picture of the breadboarded version of that synthesizer. There are some different configurations here, you'll notice, especially at the bottom there with all those little capacitors and bug-like looking ICs, the op amps. That stuff gets swapped out if you want to have your own codec. Here I'm actually taking, you can see the 2 red wires and the 2 yellow wires. Those are just analog audio coming out of the DaISY, which is the easiest way to do things rather than having your own codec. But we'll talk about all these configurations, but we're going to start at the top there at that little black connector there with the white wire coming out. That is the MIDI circuit. That's this portion, the highlighted version of the diagram here. We've got digital MIDI data coming in from the microKORG, which happens to be the only thing in my office that has 5-pin MIDI DIN. Most things in the time that I've been doing music have been USB MIDI, but that's more of a pain to hook up. This is kind of more straightforward and visceral. I don't know. It just feels good to hook this thing up. You can see here, this is the MIDI part of our circuit. We've got the MIDI signal coming out on that white wire coming out of the MIDI connector. But why can't we just connect that white wire directly into the DaISY? Why is it going into that little bug thing there, which is an integrated circuit? You'll hear about ICs a lot. There's a little circuit in that little bug-like thing with metal legs looking guy. Why does it have to go through that? Well, it's actually kind of interesting. The MIDI input circuit is a cool circuit using a lesser-known component. The whole idea of this circuit is that we don't want to have a direct electrical connection between the microKORG and the DaISY because they have different power supplies, different ground references, and you'll get a ground loop if you just plug them right together. But we want to get the digital data, digital MIDI data from one end to the other. And so here we can, by defining what digital data is, in our case, we can kind of understand how this circuit works a little bit. So we're used to digital data being bits and bytes and ones and zeros that we just kind of maybe take for granted. It's in our code, and we parse them as with some semantics, but we don't necessarily think a lot about what they physically are. To a circuit, a 1 and a 0, digital data in the physical world is just a square wave, where the 0 state of the square wave corresponds to 0 volts, and then some non-zero reference there, 3.3, I think in this case, sometimes it's 5 volts, is a logical 1. And if we can get the data from that signal and pass it from one side to the other without the electrical component, then we can achieve this goal of breaking the connection. So the component that does this is known as an opto-isolator. You won't see them too often. They're kind of rare, but they're cool. So in that black box in the middle there, right above 6N138, which is the name of this opto-isolator, 137 works just as well. It's the one that I got from SparkFun. There's that little triangle with the line under it. I don't think, pretty sure you can't see my cursor, but maybe you can. I'm just going to assume, well, we'll see. It's that little guy with the little arrows coming out of it. That is a light emitting diode. that is flashing. It is off when we want to emit a 0 and on when we want to emit a 1. And then there's a light sensitive component next to it. In this case, a phototransistor, but you might also see a photodiode there, like in the 137. As long as the main requirement here is that it converts a light signal to an electrical signal. So we've successfully generated an analogous data signal on the other end, on that RX pin that will be the DAISY, that we plug into the DAISY. We get the correct data, but it has been converted from electricity to light and then back to electricity. And it's pretty neat. This is part of the MIDI spec too. So any MIDI compliant device will have this on its MIDI input. So that's what MIDI is physically, but the semantics of MIDI are kind of part of a larger embedded systems concept that will be important for just about every project that you do. It is a special case of a serial communication protocol. So what is that? It's a very important concept, like I said, pay attention. There's, if you think about an embedded system like a series of peripheral walkie-talkies that all kind of have their one job or their set of responsibilities, anything interesting, any interesting device is going to need to, communicate between these devices, because they'll probably want to receive input, may or may not want to. But they'll almost definitely be having some sort of output that they want to send out elsewhere. Either it's a sensor that's telling the rest of the device that something has happened, or it's a CPU that's computing something. Both sides need to agree what this digital data means that's being sent between them, because it's just, again, a square wave, ones and zeros. There are a bunch of protocols that vary in the number of wires that they require and the rates that they support, and they have their pros and cons. None is intrinsically better than another necessarily. They're just, tools for jobs sort of situation. To get used to serial communication protocols, it really helps, I think, if one of your first projects is a driver for one of these. And I2C is a nice, simple one. I think it's, I can't remember. I don't want to butcher what it stands for. It's a Philips spec, though, with 2 wires. And one thing that I did early on as part of a class was do a temperature sensor. And so this is what you'll see when you are looking at documentation for these protocols. Each one of those lines there is a digital signal. So there will be 2 wires coming out of this temperature sensor, for example, and then 2 wires going into your microcontroller. The top line is the data line with the actual temperature data in bytes, or potentially integers. It depends on the bit depth of what you're sending over, but it's got the actual data. So it's, it's telling you temperatures in Celsius. And then there's a clock line under it, which is important for these kind of synchronous protocols, because the data line might be sent at a different rate, might not necessarily be stable. So the receiving end needs to know if it gets a big long 0, was there just some sort of issue that made that bit extra long, or is it actually supposed to be 2 zeros in a row? And so the clock line says, read a bit now, and now read another bit, now another bit. And so it can keep the receiving end in sync like that. The next one I want to talk about is, bringing us back to MIDI. This one is UART, or you may also see, well, you will, if you continue watching the talk, also see USART, which is Universal Synchronous Asynchronous Receiver Transmitter. The difference doesn't really matter for our purposes. All we need to know is that it's 1 wire, and then we don't have a clock line like we had with I2C. And so if the protocol is not, it's sensitive and not robust to differences in the rate of transfer. You need to be sending at a constant rate, because the receiving end will use that rate to determine when to read each bit. And the baud rate is bits per second. So that's, you'll see this often if you're setting up a console. like a little terminal that you can use to either receive characters or send characters to the device. If one side doesn't have the right baud rate, then your terminal just blows up with all sorts of garbage characters. It's a really common well, I don't know if it's a common thing for most people, but it certainly happens to me just about every time I hook this up. Anyway, it's easy to implement. It's really, there's a start bit and a stop bit, and then a data packet in between. And then the particular data type is, lives in there. We'll talk about MIDI more, but like I said, it's really popular to use this protocol early on because it's one wire and it can have ASCII characters for debugging your other subsystems pretty easily. But we can send MIDI this way. And so MIDI is commonly sent over UART. It's nice. You can set, there's a part of the MIDI spec. The baud rate is 31,250 bits per second. And so any device sending MIDI will have to send it at that rate, and any device with a MIDI input needs to expect it at that rate. And then the data packets themselves are all defined by the MIDI spec. There's node on, node off, program select, CC messages, that sort of stuff. There's a really good, I don't think it's probably worth me going too in-depth into MIDI in particular right now. There's a good write-up by SparkFun about kind of the history of MIDI, various devices and the data packets and all that. So it is an interesting topic. We're using 5-pin MIDI DIN, but you'll often see MIDI sent over USB. USB MIDI controllers are quite ubiquitous. You'll also see, I don't have any Bluetooth MIDI devices, but I've heard that that's a popular thing that's coming up, and it's pretty nifty. You'll also see it over TRS, just like a little, what is it, 32 millimeter, the little audio jack type plugs. I believe that is becoming popular in modular, though I am not yet in the modular boat, so I don't really know how true that is. But for what it's worth, DAISY's preferred mode, it seems on its website, is to send MIDI over TRS, which is kind of neat. But in our case, we are going to use the UART RX pin, a UART RX pin. I forgot if I mentioned it yet, but RX stands, you'll see it as shorthand for receive often, and TX you'll often see for transmit. So in our application, we will be receiving UART and transmitting TXing audio. And that's where the pinout comes in. A pin in an embedded context is an electrical connection between two devices that want to communicate. You can see there's pins all around the DAISY there for us to plug wires into. There's also pins, if you look at kind of third black box down is our microcontroller, the STM32. That one also has pins all around it, and Electrosmith has decided how to hook our external connections up into those pins. And so our goal is to look at all of these pins and find out where we want to connect our MIDI. You can see there's multiple UART things there in the purple boxes, various UART peripherals. But spoiler alert, as far as I know, at least in the version of the libDaisy that I was using when doing this talk, they decided pin 15 would be the one we use. We can see that one right under the audio there on the right side, under the red ones. There's UART 1 RX, but it also can be used for I2C4. And so what's up? How do we, those are very different protocols, so how do we choose? That's where GPIOs and multiplexing come in. Those pins that have multiple purposes are known as general purpose input-output pins, or GPIOs. They can be assigned to talk to different peripherals, have different functions in our code. And the whole idea is that if you just had one purpose per pin, you'd waste all sorts of space. The board would be twice as big as it needs to be. So to save space and fit this thing in a guitar pedal or whatever, something small, things are combined into these multi-purpose pins. Setting the mode of the pin is known as multiplexing or sometimes muxing, and that's something that happens in our code. So we decide the pin we want. In this case, we are the driver developers. We would be the libDaisy developers. They have decided to use pin 15, the UART RX pin, and the code will tell the hardware abstraction library how those pins should behave. They should be hooked up to UART 1. So that's kind of where the libDaisy stuff comes in. You could do this straight with the STM32 HAL, but you don't have to. The libDaisy stuff does it for you. Sets the baud rate to the MIDI spec thing, multiplexes the pins, decides which UART peripheral to talk to, and then there's kind of the other half of this, which is the data transfer. How do we actually get this data that's being sent to this pin to our program? And we'll talk about that in about 2 or 3 slides. But first, I want to talk about something that will come up. This is some of the code that is in libDaisy for setting up the UART. This is part of the MIDI Handler class. It's setting up the UART to work with MIDI. You can see 31250 bits per second being set for the baud rate, UART1 being set, but the multiplexing there happening at the bottom, setting the RX and TX pin. You can see GPIO port B for both, pin 7 and then pin 6 in port B. Didn't we say earlier, and didn't our pictures have us plugging into pin 15 and everything worked? What's up with that? You can see here, there's multiple numbers here, 15, and then there's a 14 there. What's that all about? Turns out pins are actually more confusing than maybe they should be, just kind of in all cases. You really need to just know ahead of time that the physical pin will need to be translated depending on how you're using it, whether you're in the code, and even if you're in the code, it can be a different value depending on which library you're using. So for this case, and for a lot of cases when you need to troubleshoot things, data sheets will be your friends. In this case, there are 2 data sheets that will be useful. There's the DaISY reference manual, which covers the DaISY-specific uses of the STM32, and that's where we will find a table translating all the pins in these different contexts. So if you're asking a question like, which pin do I use? That's where you would look for the answer. And while we're talking about data sheets, if you are making any changes to the drivers, and I've found that in order to make the DaISY do what you want or configure things, you do need to go into the libDaisy, into the drivers, and actually mess with the usage of the HAL. Understanding how the processor works will be very important. This I almost guarantee will be a scary document will seem like a scary document, but then if you actually know which terms to look up and you take a deep breath, it's actually not too bad. The thing's just really long, and it actually describes things, pretty well. It's just not, necessarily plain language, but it's not super cryptic either. Anyhow, the table that we're looking for here is in the DaISY reference manual, and you can see there in the second row what we saw as the physical pin 15 in our code when we're using the HAL, trying to multiplex a pin on the STM32 is actually a pin on port B, pin 7. That is our UART1 RX. So big soapbox there, but expect to be confused by pins, and then they will be less scary. So that's how we set up the pin. It's multiplexing is fun. How do we actually get that UART data to our program? There are 2 ways that are worth talking about. There's the wrong way, which is polling, and then there's the right way, which is DMA. But we'll start with polling because it's more straight ahead and easier to understand. It is a blocking call where your program running on the CPU continuously reads that register over and over again. Did we get any MIDI yet? Did we get any MIDI yet? We want to produce some great sound, but we can't do it until we get MIDI. So let's wait, not do anything else until we get it. It's a really inefficient way to do things. The CPU could be calculating coefficients, doing things other than just sitting there. But it is, sometimes, and I'm sure there are uses for it, it's just not right for this. There's a HAL call there. You can see HAL UART receive, where we pass in the UART peripheral, a buffer to fill that we want to be filled, and then the amount of data that we will wait until is filled in the buffer. Some circular language there, but there's another soapbox coming in this next slide. It turns out this polling versus just tell me when something happens so I can react to it concept comes up all the time in cases other than just reading MIDI. interesting embedded devices need to respond to stimuli of the outside world because they exist in the outside world. We need to know when we're running a coffee grinder, for example, react immediately when enough coffee has been ground so we can stop. Or, a pedestrian has pressed the walk button, so change up the lights so they can cross. High priority, block your program to do this sort of thing. This idea is called an interrupt. You may have heard of interrupts here. They are a thing in native programming a little bit, especially lower level programming, but in embedded terms, they're everywhere because responding to interrupts from sensors is how you do interesting things. They are functions, special functions that are defined by the HAL that get inserted into your program flow. Your program state is actually saved, and then the interrupt is called, and then usually your program will be written in such a way that when it returns and the state is restored, it can respond to whatever state was changed during that interrupt. That's done by the sensor actually, switching a bit in the CPU for a hardware interrupt. All the gory details are handled by the HAL, and it'll be too much of a deep dive for me to talk about like the function table that these things live in, but it is an interesting concept and will be something that you should understand well. I would recommend reading up more on it. For our cases, we're just implementing an interrupt and saying we want an interrupt to happen. So that's my soapbox about interrupts. Getting back to MIDI, we want to receive an interrupt when we receive MIDI and then respond to it rather than continuously polling for it. And that's where this handy peripheral comes in. It's called a direct memory access, or DMA peripheral. It lives off of the CPU, still on the microcontroller though, and its whole lot in life is just to send data to and from places, to and fro. The CPU initiates a request to the DMA in order to request data or to send data in other cases. And the call looks a lot similar to the polling case where we say we want to read data from the UART, UART1. Here's the buffer that we want you to fill with the data. And once it reaches this amount of data, the size, trigger an interrupt so that we can respond to it. And it looks kind of like this. It's pretty similar to the polling case, but with a little DMA after it. So with that, I think we have now gotten to our program. We need to, now that we have the ability to plumb MIDI into our program, we need to actually do something with it. And so we've got kind of three parts of our program here. We've got the initialization stage where we set up, multiplex the pins, tell the hardware what to do, whatnot. And then our program kind of flip-flops between two sections from then on until the device is powered off. It responds to MIDI and does calculations of what are called voices, which have an oscillator, some stuff in it just to generate tones. It'll either start or stop voices depending on what the message was. And then there's an audio callback, which is driven by the audio hardware saying, I want X number of samples now, and we'll just sum together all of our voices and populate a buffer of floats for it. The code looks kind of like this. I don't want to dwell on it too long here as I'm kind of running low on time, but we're starting the audio callback and then looping over the MIDI forever. Don't worry about this code. It's all in GitHub. We're responding to the note on events, starting a voice or stopping a voice, and then we've got what probably looks familiar to a native program or familiar to the use case of a native audio program. You've got an audio callback that it gets called, and we give it the state of our DSP objects. What I want to focus on is how these floats that we've returned to the audio hardware actually become real sound. That's where the SAI, or serial audio interface, comes in. But even before we get to the serial audio interface, I want to talk about what the serial audio interface is generating. We know it's generating, or it's receiving audio, but that audio is in the form of another serial communication protocol called I2S, which has audio data in the form of integers, not floats, which is important. That can be of variable bit depth, and that allows you to have more resolution in your audio signal. It has a bit clock that's similar to the I2C bit clock, which just tells you how long each bit is. And then it has a special audio-specific clock known as a frame clock or a word clock, LR clock. Basically says is the current byte that you're reading supposed to be output on channel 1 or channel 2? Left or right is sort of a misnomer, because if you stack I squared S lines for something like surround, then it'll be left, right, surround stuff. And this is kind of what that looks like. Again, it's the clock line on top, and then the word select in the middle saying how long or which channel to output on. It'll be one big long per, or one depending on if your data is interleaved or not. That the word select might have a higher or lower frequency. But that's what the digital audio data will look like. The serial audio interface, getting back to that, that's what's calling our audio callback to get those audio samples. On the STM32, it has these two blocks that have internal audio FIFOs. And basically when that FIFO is under a certain threshold, that the audio interface will trigger a DMA request. A little bit of a throwback to the CPU, but this time it's requesting data from our program. And receives all of the audio samples as floats, and actually has to scale them to the appropriate bit depth before putting them out. And that's why our program doesn't have to deal with that. We have normalized float values. And then there's an I2S stream that can be populated on one or two streams by default. In order to get that analog audio out using the onboard codec, there's internal connections from the microcontroller to the audio codec, sending that digital audio data and converting it. Or you can actually get the digital signal out on a series of pins, and we'll talk about that after this slide. I just want to show, if you're spelunking into the code, I don't want to dwell here too long, but you want to search for the SAI handler. That's what multiplexes the pins, sets the sample rate and the bit depth, and sets the clock mode. If you're messing in with this stuff, you want to be careful what the clock mode is. If you're generating your own clock, or if you're listening to a clock from some other device, the pins will behave differently and expect to either be an input or an output, depending on that. So that was a couple of days of troubleshooting for me, so word to the wise on that one. And if you're starting at the top, you can look at the DaISY seed class, which owns an audio handle, which owns the SAI handle. And all of that code is really good example code for embedded programming. That's kind of all I want to say there. This is kind of what the code is that I was just describing, but again, it's on GitHub. I want to talk about how we turn this digital audio data into analog, though. That's pretty important. Many of us have dealt with digital to analog conversion before, but you do have to think about it kind of in a different way than you might be used to in circuitry, because there is audio data in two different forms in your circuit. There is an analog signal that is coming out of it, which is an alternating current, and then there is, audio in the ether, known as digital data, which is ultimately supposed to, when it becomes useful, in our case, be turned into an analog signal. And so it's a series of voltages that will be output as an AC signal. Each one of our audio samples corresponds to an analog voltage, and then the depending on what your bit depth is set to, you get this weird kind of aliasing or less resolution if your bit depth is too low, because the same value will correspond to multiple voltages. And then the digital to analog converter knows how to output those voltages at a fixed rate and then drive a speaker. I want to talk about codecs real quick, kind of what they are, because in the embedded space, you'll hear codec come up all the time, and it has nothing to do with compression and decompression like MP3, which is also a codec in software. It's mostly a shorthand for a peripheral that has both, usually an ADC and a DAC, or one or the other, and sometimes has an amplifier on it. So when you hear codec in the embedded sense, think that at first. Like I said earlier in the talk, there's an internal codec. At one point, it was the AK4556. I don't know if it still is, but that's where those two audio pins come out there that arrow is pointing to. Or you can multiplex and set up the digital pins there to connect to your own codec. So having the internal codec situation kind of looks like this, where you've got the analog audio coming straight out of the DaISY, being amplified there. There's a line out on the left going to that quarter-inch jack, or there's a stereo amplifier there at the bottom with those LM386, which I don't have a lot of time to talk about, but it's an op amp. Check out this Tales from the Chip article for more information, because it is good when you're setting up your lab to have a bunch of those LM386s lying around just to amplify signals as needed without needing a bunch of expensive hardware or anything. The other configuration you can do if you want to take the digital signal and use your own codec, you can get one of these I2S breakout boards, and you'll need to do this if you use a different type of SOM like the TNC or something that requires a external hardware. You'll take the digital data that comes out of your board and use something like this to convert it to analog, and then you can play the synth, which I'll do here. So, it's got some artifacts there, especially if you had things turned up. But, for 200 lines of code, it's pretty nice. Some sources of noise you'll find out just kind of as an aside. Debugging that noise, sometimes it's in the analog realm. The other day I had the noise that you heard there at the end of that clip, but it was really loud. And I was able to fix it by just changing how ground was configured. It was, over all these wires, and dealing with that stuff and debugging it is very different from native stuff, and it's a cool little mind game. But anyway, going over this synth again, just in the last couple minutes, you've got the MIDI going in here from the microcord, coming in as a digital signal. We interpret it as a UART signal that goes through this little opto-isolator circuit, gets turned, remember, from electricity into light and then back into electricity as ones and zeros, sent on this little green wire into pin 15 on the DaISy. We multiplex that pin to accept UART. There, going back, our program then generates audio in response, and then those three wires there are outputting an I2S signal going into this codec here, which is converting the audio into analog, amplifying, being sent to a speaker. So what's next if you're interested in doing this sort of stuff? The DaISy tutorials are great. If you could take this synthesizer and use those tutorials to add things like knobs, learn about ADCs, the ADCs in the knob sense that drive your program, that sort of stuff. Like I said before, Make Electronics is great for setting up your lab, buying components, learning about things like Ohm's law, the fundamentals of electricity, all that stuff. Alicia White has a great book that is much more useful than this talk that I just gave in terms of actually learning the industry standard practices for embedded programming. It kind of goes all the way through power management and optimization and that sort of stuff. And then if you're interested in Linux, I would definitely recommend this book. It'll have you write a program, bundle it in your own, roll your own Linux, and then do the same thing with Yocto, same thing with Buildroot. And after reading that book, I was able to, get some crap done at UA on the embedded Linux devices there. So that was a very useful resource. Beyond books, I would recommend learning about breadboarding, and definitely set up a power section. This is just kind of I would call it a pro tip if I was a pro, but I'm not. So just a tip, set up a power section on your breadboard. I was lucky enough to have a DC power generator when I was doing this stuff in school, but you can set this up with some little components. I might maybe do a little blog post and a schematic on this, because for like $5 you can not have to continually plug things in and out from the wall. You always know there's power. Otherwise, you'll always be wondering, why is there no sound? Oh, it's because the power, doesn't work right now. It's very useful to have that for your sanity. Then pick, are you going to use the Arduino, the TNC, the DaISy? What are you going to build? It all depends on what you've got available and whether you want to have an internal or external codec, that sort of stuff. And then build one of these things, build something that you've always wanted to build. Kind of start with the I/O. That's kind of a good place to think about what your constraints will be. You can do anything. And we're right here under 50 minutes. Feel free to email me, Twitter. I'll share the GitHub repo in these slides, and have a great ADC. Thanks, everyone.